We propose a novel method that computes the relative pose and common focal length between two frames of a vehicle-mounted camera. The paper is written by Levente, Hajder and Barath. The presenter is the first author. The estimation of camera pose between two images is essential for both robotics and computer vision. The main novelty of our paper is that we exploit not only point correspondences, but affine transformations are applied to compute spatial information. Our approach assumes planar motion. In this case, the camera is mounted on a vehicle, the image planes are perpendicular to the ground, and their vertical pixel directions are parallel. The main application area of our method is machine vision for autonomous driving. Here is an example to visualize why affine transformations that are scales, rotations, and shears are useful for 3D vision. The camera is mounted to a car. There are two images. In the right one, the car is closer to the lamp. Different surfaces are marked in the images. In the left image, the area of the backsides of the other cars waiting for the green lamp are visualized. A few walls of distant buildings are also marked. It's clearly seen that the areas of the backsides are significantly larger in the right image, while the changes in the areas of building walls are not significant. This example suggests that the scale itself encodes information of camera object distance. This is a stereo setup. There is a surflet. Their projections are quadrilaterals in the images. The centers are drawn by dots. The surflet is represented by its spatial location and normal vector. Standard 3D vision algorithms deal with locations in the images. They are colored by red. Each location in the image determines a projecting ray, and the spatial location of the surflet is in the intersection of the projecting rays. This spatial estimation is called triangulation in the literature. However, if affine transformations are considered, not only the spatial location but the surface normal can be retrieved. Therefore, the tangent plane of the surface can be computed if corresponding point locations and the related affine transformations are given. The seminal work for processing affine transformations for 3D vision was developed by Kevin Koeser in 2009. Since that, researchers, including us, have shown that several tasks can be solved by affine transformations: surface normal homography, essential and fundamental matrix estimation, calibration of camera parameters. Moreover, a full 3D pipeline with bendel adjustment as a final step can also be formed based on affine correspondences. In stereo vision, camera pose, that is the relative rotation and translation of two images, are usually encoded in the elements of the essential matrix. It can be formed as the product of the so-called cross-product matrix of the translation and the rotation matrix. For the uncalibrated case, only the fundamental matrix can be estimated, that comes from the relationship of the essential matrix and the intrinsic camera parameters. If only point correspondences are applied, each location pair gives one equation for the estimation of fundamental or essential matrices. For the fundamental matrix estimation, at least 8 point correspondences should be given. If the cameras are calibrated, only 5 correspondences are needed, as the elements of the essential matrix should fulfill the singularity and trace constraints. However, affine transformation can also be utilized for the estimation. If there is a spatial direction represented by vector t, and it is projected to the images, the affine transformation transforms the directions v and v prime between the images, where v and v prime are the projections of spatial direction. The author of this paper have shown that for stereo vision, an affine transformation transforms the perpendicular direction to the epipolar lines into each other. Moreover, the scale can also be calculated using the affine transformation. This fact can be written by this two-dimensional vector equation. It adds two equations for the estimation of the fundamental matrix. For the calibrated case, the same equation is valid for the essential matrix if the point locations are normalized. The main goal of this presentation is to show how the aforementioned three equations, one for point location and other two for affine transformation, can be utilized for estimating the pose for planar motion. In this case, the relative motion can be written by two parameters: the rotation around vertical axis, represented by angle alpha, and the direction of the translation. The essential matrix consists of 4 non-zero elements. However, they can be written by the two unknown angles alpha and beta. The semi-calibrated case is considered here. A camera is semi-calibrated if its principal point is known, it is in the origin of the coordinate system and the image space. Moreover, the shear must be 0 for the camera, and the horizontal and vertical focal length should be equal. Focal length is the only one unknown intrinsic parameter of the camera. For the proposed method, the first and second focal lengths should be the same. For our setup, the fundamental matrix, similarly to the essential one, consists of 4 non-zero elements. They are functions of the 3 unknown parameters, 2 angles and the common focal length. As it is well known, the scale of the fundamental matrix is arbitrary. This problem can be written as a homogeneous linear system, thus the null vector of a 3×4 matrix should be computed first. Then the 3 parameters can be trivially obtained from this null vector. We consider only the minimal case when 3 equations should be given. This is possible if only a single affine correspondence is given. Robustification is also an important issue, as the affine matchers often fail, therefore the input data for our method are contaminated with outliers. Note that the calibrated case is also very important when the focal length is known as well. We propose an optimal algorithm even for the overdetermined case. For details, see our other paper in this conference. For the synthesized test, granted noisy data are generated by MATLAB. For the camera pose, the planarity constraint is considered. 50 random points are projected using the random camera parameters. Gaussian noise are added to both point locations and affine transformations. The proposed method for the first test in the first row, then the camera parameters are known, is compared to the 5-point algorithm of Stevenius, the 2-point method of Choi et al., and the simple linear 3-point algorithm. The proposed method is denoted by 1AC, as only one affine correspondence is required for the estimation. Our method shows comparable accuracy to the 5-point method. Other algorithms are significantly less accurate, especially for the rotation estimation. In the bottom row, focal length estimation are compared. Here, the 6-point method is the best one. Remark that the main benefit of our method is that it requires only a single correspondence. In this slide, special motions are considered when there is no rotation. In the first case, in the top row, the camera moves forward. For the second test, in the bottom row, the camera moves only to left or right. The conclusion is similar to that of the previous slide. The accuracy of our method is similar to that of the 5-point algorithm. For real tests, we have downloaded the Malaga dataset containing more than 10 kilometers video. Every 10th frame is selected from the video, and our pose estimation is run for each consequent image. Then the motion trajectory is built by concatenating the poses. We have drawn the estimated trajectory next to the input video on the right side. The trajectory is pre-computed. This video shows that the accuracy of the estimated trajectory is satisfactory. The turnings are correct as it is seen here, where the car turns right. The method is not sensitive to the quality of the images. In this treat, the sun is in front of the camera. The contrast of the image is extremely low in some frames, and there are white regions in the images due to the sunlight, as it is seen here. However, our method is robust enough to cope with such challenging situations. We have drawn the estimated trajectories to the corresponding map. Here, the grand truth trajectory given by a GPS is colored by yellow. The proposed algorithm is robustified by both histogram voting, purple line, and GraphCat Rensec colored by red. The competitor algorithms are the standard 5-point method and the simple 3-point linear method for planar motion. We suggest the application of histogram voting as the results are better compared to the Rensec light robustification. Let me conclude the work. We have shown that a single affine correspondence can be applied to estimate the relative pose of a stereo setup if planar motion can be assumed even for semi-calibrated cameras. An affine correspondence gives 3 equations to 3 unknown parameters, 2 angles, and the focal length can be estimated. The proposed approach extends standard point correspondence-based ones by exploiting affine transformations. Our solver is based on a linear system of equations. It can be efficiently solved, and the robustification is efficient as well. Finally, let me enhance the benefits of affine correspondences. We have shown that the pose for a planar stereo setup can be solved for a single correspondence. Moreover, the tangent plane can also be computed from this correspondence. Thus, oriented point clouds, that are points with normal directions, can be computed. This means that a full 3D reconstruction, including the camera calibration, can be computed from only one correspondence. Therefore, only local information is required, contrary to the point-based algorithms, where at least 2 points are needed, and these 2 points shouldn't be close to each other. Therefore, point-based approaches are global methods in the sense that they require distant correspondences, contrary to our method, where 3D camera and structure parameters can be computed from local data. And finally, thank you for your attention.